So how do we handle trig integrals? Well, we've got our standard integrals that we already know. So sine goes to minus cos, cos goes to minus sine, sec squared goes to tan. Tan, remember, could be written as sine on cos, which gives you minus the log of cos or the log of sec, depending on what you prefer. Okay. What about if it's sine or cos to the power of something? I'll just do sine, because cos being a complementary ratio, basically it's the same technique. So I'll just do the sine ones. So if we start off power of 1, okay, fair enough, standard integral, minus cos x. Sine squared, well, we've seen how we handle that one. That's where we use our trig identity, change that to a half of 1 minus cos 2x. Remember, cos squared would be a half of 1 plus cos 2x. And then we integrate each of those individually. Okay, so there's sine squared. Sine cubed then, sine cubed. Well, what I'm going to do with sine cubed is I'm going to rewrite sine cubed as sine times sine squared. What that allows me to do is change the sine squared to 1 minus cos squared. And now I can do a substitution, because sine is the derivative of cos. Now, whether you actually do it via a substitution or you just see it straight away and you notice, oh, I've got derivative times function, I mean, that's up to you. But basically we've got u equals cos x, so du is minus sine x dx. So I get minus 1 minus u squared du. Add 1 to the power over the power, subbing the cos back in, and there's my answer, 1/3 cos cubed minus cos. Now that idea, whenever sine is to an odd power, I'm going to use this idea. Because whenever it's an odd power, I can always factorise sine x out. Right? That'll end up becoming the du. And write it as sine squared to some power. Because once I factorise out the sine, it's now going to become an even power. So therefore I can write it as sine squared to the power of something. Then the sine squared I can always change to 1 minus cos squared, and then use the u equals cos x. So I can use that idea anytime the power is odd. Let's keep going. Even. Can't use that idea now, because if I use that idea, I'm going to have sine x outside of sine cubed. And that gets a little bit messy, because sine cubed, what do we write it as? Sine squared to the power of, and you got fractional powers, and there's an easier way. Well, it's already an even power, so I'm going to write it as sine squared squared. But this time, instead of saying sine squared is 1 minus cos squared, I'm going to use the double angle relationship and say, well, that's a half of 1 minus cos 2x. But I'm squaring it, so I get a quarter 1 minus cos 2x all squared. Then I can expand out the 1 minus cos 2x, and each of those individual bits I can go and integrate. So before I integrate, notice I've now got a cos squared x in there, so that cos squared I've got to change to a half of 1 plus cos 4x, double angle. Now I can go and integrate, and each of those pieces integrate nicely, so the cos just goes to sine. So that's what I'll do when it's an even power. I won't bother factorising out the sine. I'll straight away say it's sine squared to the power of something, and then use the double angle substitution for sine squared. So therefore, sine 5, well, that's odd. So I'll factorise out the sine. I can write that as sine squared squared. The sine squared, I'll use the 1 minus cos squared for this one. And now I can use u equals cos x. And I've got 1 minus u squared squared, which is just a polynomial to expand out. Add 1 to the power over the power, sub back in. So the odd powers I think are a lot quicker. I don't think I bothered doing sine to the 6, but that's the next even one. When you expand out the even ones, you generally have to do another substitution in there. Like I did with the power of 4, I had to use the double angle result again. Okay. What happens if I've got a combination of both? I've got sine to the power of something and cos to the power of something. Generally, we're going to do it by a simple substitution, u equals sine x or u equals cos x. Do it by means of some examples. But I've got cos to the power of 5 and sine cubed. Okay. I'm going to rewrite the sine cubed as 1 minus cos squared times sine x. Same idea. If I can get that sine to an even power, then I can write it as sine squared to the power of something, substitute in the 1 minus cos squared. So I want to pull out sine x as a factor. I could have done with cos as well, you'll notice, because if I pulled out cos x as a factor, I would have got cos to the power of 4, which I could have written as cos squared squared and changed the cos squared to 1 minus sine squared. When I've got a choice like that, I always go with the lower power. So cubed was the lower power, so that's the one I changed. So u equals cos x to u minus sine x. Substituting in, again we just get some polynomials to play with, and there's our answer. So as I was saying, if both the powers are odd, it does not matter which one you choose as the u. Choose the higher power as the u, which means it's the lower power that you're going to rearrange. So the higher power was the cos, so that made u equals cos x. That meant I needed to pull out the sine x as the factor, which was the lower power. Okay, so that's both odd. One even and one odd. Well, if one's even and one's odd, then I know straight away I'm going to play with the odd one, because the same idea. I can pull out a factor of cos x in this case, leave it with cos squared. Cos squared I can change to 1 minus sine squared and do the substitution. In this case, u equals sine x, so du is cos x, subbing in, add 1 to the power over the power. So alright, if one's odd and one's even, the even one is going to be my u, which means it's the odd one I'm rearranging. So the odd one is the one where I'm going to pull out the factor to the power of 1, and it'll become the du. Which leaves us with the possibility that both are even. Now of course if both are even, I can't pull out the single factor of the cos x or the sine x. So this one here, I change the cos squared to 1 minus sine squared. Because if both are even, I can change it to the other one. Now it doesn't matter which one I pick. Now in this case they were both squared, so it really didn't matter which one I picked. But I could have changed the sine squared to be 1 minus cos squared, and then I only have coses. But what I'm left with is just like my first case, where it's just sine to the power of something. And then we have a technique to deal with sine to the power of something. Sine squared, and I think I've cheated a little bit here, because we already did those, so rather than me working them out again, I've just written down the answer I got before for sine squared and sine to the power of 4, and then I just pull that all together. Okay. So when they're both even, you're either going to use sine squared equals 1 minus cos squared equals 1 minus sine squared. Again, I would rearrange the lower power, because that's going to be the easier expansion to do. In this case it didn't matter because they were both equal to 2. What about if I've got tan, or cotan for that matter, to the power of something? So again, I'll do the tan ones. They're complementary ratios. The technique's the same as we go through. So tan, I now know that's minus the log of cos or the log of sec, depending what you prefer. So that's tan to the power of 1. Tan squared, well tan squared I can rewrite as sec squared minus 1. And we know that sec squared integrates to give tan, and 1 obviously integrates to give x. So squared's not a huge problem. Tan cubed. What am I going to do with tan cubed? Okay. It looks like I've factorised out the tan x, but I haven't. What I've actually factorised out is the tan squared. Effectively it's the same thing, but the important bit is the tan squared, because it's the tan squared I'm going to change to sec squared minus 1, and I can split that into two integrals. Now one of those integrals will be times tan x, so I'm going to have tan x times sec squared. Sec squared is the derivative of tan. It's going to work out nicely, and the other one's just minus tan x, and I know the answer to that. So I'll do u equals tan x, and I get integral of u du minus tan x. And so I get half tan squared plus the log of cos. So tan to the 4, same again. Tan squared I'm pulling out. and changing it to sec squared minus 1. So it doesn't matter whether it's odd or even. I'm going to use the same technique every time for tan. Split it into two integrals, and now I've got tan squared sec squared. Well, that's okay, because sec squared is the derivative of tan. So now it's just, the left one's now just going to be u squared. The right hand side I've got tan squared, and well, we've worked out an integral for that before. So the right hand one, depending on what power you're playing with, you might have to use the technique again and again, depending on the power. So u is tan x du is sec squared, so my left hand integral u squared du, right hand integral tan squared, but tan squared we worked out earlier, so again I just substituted that in rather than working it out again, and a third u cubed becomes a third tan cubed. Integral of sec. Now, integral of sec, what I'm going to do is multiply top and bottom by sec plus tan. And you'll look at that and saying, well, how on earth would you think of that? And the answer is you wouldn't. But now you will, because you've seen it now. So why do we do that? Look what happens on the top. You get sec squared. Well, sec squared is the derivative of tan x. And you get sec tan, and sec tan is the derivative of sec. So you've actually got derivative on function. So it becomes the log of sec plus tan. Personally, I just remember that the integral of sec is the log of sec plus tan, rather than do that each time. But that's where it comes from. So you multiply top and bottom by sec plus tan and the answer drops out. So there's sec x. Sec squared is easy because we know that's just tan. It's a standard integral. Sec cubed. Sec cubed. Sec cubed I'm going to factorise out. There's my sec squared times sec. I'm going to do a u equals sec x, because then du becomes sec x tan x. Hang on. What on earth are you doing? Well, that means dv. That's right, I'm doing it by parts. That means dv is sec squared and v is tan x. So uv minus integral of v du, but now v du is sec x times tan squared x. Okay, so the tan squared I'm now going to change to sec squared minus 1. That now makes it the integral of sec cubed plus integral of sec. Well, integral of sec I know, that's the log of sec plus tan. I've got integral minus integral of sec cubed. Well, that's what I'm trying to find. So now it's one of those ones where, hey, I'm now going to treat it like an equation rather than a whole heap of working out. I'll move that integral of sec cubed to the other side. 2 times the integral of sec cubed, so therefore divide everything by 2, and we have our answer for sec cubed. So sec cubed I'm going to do by parts. Whenever you've got an odd power for sec, you're going to end up doing it by parts. Even ones are so much nicer, because look what you can do with sec to the 4. I can pull out the sec squared, change it to 1 plus tan squared, but hang on, sec squared is the derivative of tan. I can just do u equals tan x. Oh, it's 1 plus u squared du. Bingo, there's our answer. So whenever you're doing a test, you're praying for an even power of sec rather than an odd power of sec. Okay, so even powers, you can always pull out a sec squared. You'll end up with sec squared to some power, and then you can do that substitution. There's our exercises.